All right, so today we're going to be taking a deep dive
Okay.
into the world of machine learning,
Sounds good.
specifically how language models are being taught to reason more like us humans.
Mm-hmm.
I think this is going to be a really interesting one.
Definitely.
The research that we're going to be looking at today comes from a paper
Okay.
titled Quiet-STaR.
Oh, wow.
Language models can teach themselves to think before speaking.
I like that title.
Yeah,
Very catchy.
it is catchy and it's accurate.
Right.
So before we really get into it, can you just give us a super brief
Yeah.
explanation of what we're talking about here when we say reasoning in language models?
Yeah. So, it's kind of moving away from just having a language model like generate text, right? So it's not just about like spitting out the next word or,
Yeah.
the next sentence. It's actually like understanding the why behind statements and things like that. It's
Right.
really understanding what's going on.
So not just like grammatically correct, but like logically makes sense.
Exactly.
Yeah.
Yeah. More than just being grammatically correct.
So this Quiet-STaR, that's a really interesting name.
Yeah.
What is that all about?
Yeah, so the idea here is that they're training language models to generate these like internal thoughts.
Yeah.
Internal thoughts. Internal thoughts, almost like a silent internal monologue to help them better predict the upcoming text.
So it's like thinking before they speak.
Yes, exactly.
That's a good way to put it.
So how is this different from how language models have traditionally been trained to reason?
Yeah, so traditionally, a lot of the time, people have used like carefully curated reasoning data sets.
Okay.
But Quiet-STaR actually leverages just the vast amount of unstructured data on the web.
Okay, so all that crazy stuff.
All that crazy stuff out there.
Yeah.
All the text and everything is fair game now.
So instead of having to like really neatly package all the training data,
Right.
it's just kind of like throw everything at it and let it figure it out. Exactly, and see what it can learn from all that mess.
That's fast
Yeah.
there.
Yeah.
Okay, so we have these models now generating these like internal thoughts,
Mm-hmm.
like silently thinking to themselves.
Yeah.
But I'm immediately thinking, okay, so if it's generating these thoughts for like every single
Yeah.
word or token in a text, wouldn't that be incredibly computationally extensive?
Yeah. You're absolutely right. That
Yeah.
would be a major bottleneck.
Like, it just seems like that would be impossible.
It would take forever.
Yeah.
So what they did was they actually developed this parallel sampling algorithm. So instead of processing each token sequentially,
Mm-hmm.
it actually allows the model to explore multiple reasoning paths simultaneously.
So it's like instead of thinking one word at a time, it's thinking like in parallel.
Exactly. It's like juggling multiple thought processes at the same time,
Okay.
trying to see, okay, well, what are the connections here?
And that must just speed things up a ton.
Oh, yeah, definitely.
So much faster.
That makes sense. So I'm looking through this paper.
And I'm seeing these meta tokens.
Mm-hmm.
What are those all about?
Yeah, so these are really important. Basically, think of them as like special instructions for the model.
Oh.
So they use these learned meta tokens. They have like a start of thought token
Okay.
and then an end of thought token.
Okay.
And so basically, when the model encounters the start of thought token, it's like, okay, I need to start generating a rationale here.
Okay.
I need to start thinking. And then when it hits the end of thought token, it's like, all right, thinking time's over.
Okay.
Back to predicting the next word.
So it's like a switch in the model's brain.
Yes, exactly. It's like flipping a switch.
Okay, flip it on, flip it on.
Yeah, yeah.
Now this is where it gets really interesting for me.
Okay.
They initialize these tokens
Yes.
using the embedding for an M dash,
Yeah. So smart.
like the little dash that we use.
Yeah, like a pause in
Yeah.
writing or a break.
Okay, so it's like already kind of inherently knows.
It already knows.
Yeah,
Yeah, that's a pause or a break.
like it already knows that this is like
Yeah.
a place to stop and think.
Yeah, it's like building upon the model's existing knowledge of like human language and how we use these pauses and breaks.
Oh, that's super clever.
Yeah.
Okay, so you've got these models generating these internal thoughts,
Mm-hmm.
but how do they like integrate that
Yeah.
with their actual predictions? Like,
Right.
is there some kind of mechanism?
Yeah. So that's where this component called the mixing head comes in.
A mixing head.
Mixing head.
Okay.
Yeah. And basically what it does is it learns to balance the model's predictions with and without the generated thoughts.
So it's not just like blindly accepting whatever thought.
Exactly.
That
Yeah.
part.
It's like a gatekeeper
Yeah.
saying like, okay, how much weight should we give to these thoughts versus just like the model's initial instincts?
And how does it learn that?
So it learns it through the training process.
Okay.
And basically, it's trying to find the best balance
Okay.
to improve the overall accuracy of the model.
So at first, when the model starts generating these thoughts, they're probably not.
They're probably pretty random.
Yeah.
Like, not super helpful.
Yeah.
But over time, as the model learns,
Right.
the mixing head also learns to better integrate those thoughts and make sure that they're actually contributing to the accuracy of the model.
So it's like the model is learning to trust its own thoughts as it gets better
Exactly.
at thinking.
Yeah.
Interesting.
Yeah.
Now, this is where it gets kind of wild to me.
Okay.
The paper talks about how Quiet-STaR is trained
Yeah.
using a reinforcement learning technique called reinforce,
Mm-hmm.
where the model gets rewarded
Yeah.
for making good predictions.
Right.
But they specifically mention that they ignore negative rewards,
Right.
like if the thoughts actually hurt the prediction.
Interesting choice.
Yeah, it seems kind of counterintuitive, doesn't it?
Yeah. Like, why wouldn't you penalize the model for making a mistake?
Yeah.
But what they found was that actually ignoring those negative rewards
Okay.
leads to a more stable training process. Because if you think about it, like, if you're constantly penalizing the model
Yeah.
for these early kind of like clumsy attempts at reasoning,
Right.
it might discourage it from exploring,
Okay.
and it might prevent it from developing its reasoning abilities.
So it's like giving it space to be wrong
Exactly.
at the beginning.
Yeah, you got to let it make mistakes
Okay.
to learn from them.
So they're not totally ignoring the mistakes.
No.
It's just that they're not like actively punishing.
They're not like whacking it over the head
Okay.
every time it gets something wrong.
Got it.
They're just saying, okay, let's focus on the positive.
So it's like more encouragement
Yes, exactly.
rather than punishment.
Yeah, positive reinforcement.
Interesting.
It seems to work.
Yeah, I'm really curious to see
Yeah.
where this goes.
Me too. This is cool stuff.
yeah.
I like this.
Okay, so the paper highlights some pretty impressive results
Mm-hmm.
in terms of like the model's predictive power.
Yes.
Can you tell us a little bit about that?
Yeah. Yeah. So they found that this approach actually leads to significant improvements
Okay.
on standard language modeling benchmarks.
Wow.
So it seems like these internal thoughts are actually giving the model like a deeper understanding of the text,
Okay.
allowing it to like anticipate what comes next.
Okay, so it's not just like statistically
Right.
predicting the next word. It's like
It's actually getting,
actually understanding the
Yeah.
meaning.
yeah,
Okay.
it's understanding the nuances.
okay.
It's understanding the implications of what's being said.
That's really cool.
Yeah, it's very cool.
So how do they actually measure this reasoning ability?
Yeah, that's a good question. So they're not actually using like specific reasoning tasks for evaluation.
Oh, yeah.
What they're doing is they're looking at the model's overall accuracy
Yeah.
in predicting text.
Okay.
So the idea is that if the model is reasoning effectively,
Yeah.
it should naturally lead to better predictions across a wide range of texts.
So like if you can consistently predict what comes next,
Ex-
you must be doing something right.
You must be getting it.
You must be understanding.
Yeah,
Yeah.
you're figuring out the logic of the
Okay.
language.
So what were the actual results?
So they found that Quiet-STAR led to significant improvements
Okay.
on standard language modeling benchmarks.
That's awesome.
So that suggests that this internal thought process
Yeah.
is actually boosting the model's overall language comprehension.
Okay, so it's actually working.
It's working.
Yeah.
Yeah.
It's not just like a cool idea. It's like
That's not just a theory.
Yeah.
It's actually producing tangible results.
Okay, cool.
Yeah.
So given all this internal processing, are there any like
Yeah.
limitations to this approach?
Yeah. That's a really good point. One of the main limitations right now is that it is computationally intensive.
Right.
So it's not really practical for like smaller scale applications at this point.
Okay.
And another thing is that right now the model is generating thoughts for every single token,
Okay.
which might not always be necessary.
All right, so there's room for optimization,
Yeah,
like
definitely.
figuring out when those thoughts are most valuable
Exactly.
and when they're maybe not needed.
Yeah, when it's overkill.
Yeah.
Yeah.
So
Yeah.
what could that look like?
So one idea that they're exploring is actually training the model to predict when it needs to generate a rationale.
Okay.
So instead of doing it for every single token,
Mhm.
it can learn to be more selective.
So it's like learning to recognize when something is hard.
Exactly.
Yeah, no.
And when it needs to actually think about it more deeply.
That's fascinating.
Yeah,
So it's like the model is learning to be more efficient with its own thinking.
exactly.
Wow.
It's like metacognition for AI.
Whoa.
Yeah.
Metacognition for AI. That's crazy.
I know, it's like AI thinking about thinking.
I love it.
Yeah, it's pretty wild.
All right, so this is really interesting.
Yeah.
I'm already like blown away by this.
Me too.
So next time we're going to actually look at
Right.
how they train the model
Sounds good.
to generate these helpful rationales.
Let's do it.
And we'll see how it performs
Awesome.
on some reasoning tasks.
I'm excited.
All right, we'll see you next
Thanks,
time.
Salmon.
All right. All right. Okay, so we're back.
All right.
And we left off talking about
Yeah.
how Quiet-STaR uses reinforcement learning
Mm-hmm.
to kind of reward the model
Yeah.
when it makes good predictions.
Right.
But now I want to know, how do they actually train the model
Okay.
to generate these helpful rationales?
Yeah, so it's not just like random thoughts, right?
Right.
There's actually a method to the madness.
Okay.
And it involves this technique called teacher forcing.
Teacher forcing.
Teacher forcing.
Okay.
So basically, during training, the model is given the correct next tokens as input, even if its initial predictions are off.
Oh, so it's like they're giving it the answer?
Kind of, yeah.
Okay.
So it's like they're saying, okay, we know you're still learning,
Okay.
but here's a little cheat sheet to help you along. See if you can figure out how to get to the correct answer.
So it's like instead of just letting it make mistakes,
Right.
they're kind of guiding it.
Exactly. They're giving it a little nudge in the right direction.
So how does that actually help the model learn?
So by providing those correct answers, it's kind of like giving the model a roadmap to follow,
Okay.
right?
Yeah.
So it can connect the dots between its thoughts
Yeah.
and the desired outcomes.
Okay, so even if it gets the first step wrong,
Right.
you're still kind of showing it.
Exactly. You're still shown it the path to the right answer.
Okay.
Yeah.
So this teacher forcing, does it actually work?
Yeah, it seems to be pretty effective.
Okay.
They found that it significantly improved the quality of the model's rationales,
Okay.
making them more logical and coherent and relevant to the task at hand.
That's awesome.
Yeah, it's pretty cool.
So how did they actually test this whole thinking before speaking thing?
Yeah, so they evaluated Quiet-STAR on 2 different data sets
Okay.
that are known for requiring reasoning.
All right. One is called CommonsenseQA,
Okay.
and the other one is called GSM-8K.
All right, so what are those all about?
So CommonsenseQA basically tests the model's understanding of everyday knowledge.
So like common sense.
Like common sense, yeah.
Okay.
And then GSM-8K focuses on solving grade school math problems.
Okay.
Yeah.
And how did Quiet-STAR do?
So on CommonsenseQA, it actually boosted the model's performance from 36.3% to 47.2%. Wow, that's a huge jump.
That's a big jump, yeah.
Okay.
Especially considering that the model was never specifically trained on that data set.
So it was able to apply what it had learned.
Exactly.
So it was able to generalize.
To this new set of problems.
Yeah, it's pretty impressive.
That is impressive.
Yeah.
And how about GSM-8K?
Yeah, so on GSM-8K, it also did really well.
Okay.
It helped the model jump from a 5.9% accuracy to 10.9%.
Wow, okay.
So another big improvement.
Yeah.
And again, this was zero-shot performance.
Right. So it had never seen these problems before.
That's crazy.
Yeah, it's pretty wild.
So this Quiet-STAR, it's not just about
Right.
predicting the next word.
Exactly. It's about actually solving problems
Yeah,
that require logical thinking and reasoning.
like actual problem solving.
Yeah, it's getting there.
Okay.
It's on its way.
Now, there's one finding
Okay.
in the paper that I find particularly interesting.
All right, what is it?
So they found that Quiet-STAR doesn't necessarily improve predictions for all tokens,
Okay.
but it disproportionately helps with the tokens
Yeah.
that are the most difficult to predict.
Interesting.
Yeah.
So like it's focusing its energy.
Yeah, it's like it knows where it needs to think harder.
Exactly. It's like it's learning to be strategic with its thinking.
Wow.
Yeah.
So is this like evidence
I think so.
that it's actually like reasoning?
Yeah, it seems like it's engaging in more complex reasoning
Okay.
when faced with those challenging predictions.
So it's not just like a fluke.
No, it's not just like a statistical trick. It actually seems like it's understanding.
It's thinking.
It's thinking, yeah.
Wow. Okay.
It's pretty cool.
So there are other methods out there
Mhm.
for enhancing reasoning
Right.
in language models,
Yeah.
like chain of thought prompting.
Yeah.
How does Quiet-STAR compare to that?
Yeah, that's a great question. So it turns out they're actually quite complementary.
Really? But aren't they both trying to get the model to think?
They are, but they go about it in different ways.
Okay.
So with chain of thought prompting,
Yeah.
we're explicitly asking the model to think out loud,
Okay.
right? Like generate a series of reasoning steps that lead to its final answer.
So it's like show your work.
Show your work, exactly.
Okay.
Whereas with Quiet-STAR, it's more like encouraging the model to think silently,
Okay.
like generate these internal rationales without explicitly stating them.
So like the difference between thinking aloud and thinking to yourself.
Exactly.
Oh.
Okay, one is explicit and the other one is more implicit.
And can they work together?
So what they found was that actually combining the two approaches
Okay.
leads to even better performance.
Wow.
Yeah. So it's not an either-or situation.
So you can have those internal thoughts
Yeah.
and then the explicit chain of thought.
Exactly.
Wow.
Yeah.
Okay, that's amazing.
Yeah, it's pretty cool.
So it's like Quiet-STAR is laying the groundwork.
Yeah, it's like building a foundation.
Yeah.
For reasoning.
And then chain of thought and prompting is kind of building on top of that.
Exactly.
We're teaching the model to think in multiple ways.
Yeah, we're giving it multiple tools.
Wow. That's fascinating.
It's pretty cool.
Okay, so the main focus of Quiet-STAR is on improving the model's accuracy.
Right.
But the paper also hints at another potential benefit.
Okay, what's that?
Interpretability.
Yeah.
Can you tell us a little bit about that?
Yeah, so while these generated thoughts might not always be perfectly coherent
Okay.
or easily understandable to us humans, they do offer a glimpse into the model's internal reasoning process.
We can kind of see what it's thinking.
Kind of, yeah. It's like peeking into the mind of a machine.
Ooh.
Yeah.
That's a little scary.
It's a little bit scary, but it's also really exciting.
Yeah.
Because it means that we can start to understand how these models are arriving at their conclusions.
Okay, so even if we don't totally understand it,
Right.
it's still like a step towards
It's a step towards interpretability.
understanding.
Yeah. We're moving away from that black box.
Okay.
Yeah.
So why is this interpretability important?
So it's really important for building trust in AI systems, right?
Yeah.
Because if we can understand how these models are thinking, then we can better assess their reliability.
Yeah, okay.
We can identify potential biases,
right.
and we can make sure that they're being used ethically and responsibly.
So it's not just about like
Right.
making sure that they work.
It's about making sure that they work in a way that we're comfortable with.
Right. And that we understand.
Exactly, yeah.
Yeah, that's really important.
It's crucial.
Okay, cool.
Yeah.
So the paper gives some examples where the model's thoughts seem to actually reflect understanding.
Yeah.
But it's important to remember that this is still early research.
Oh, yeah, definitely.
Oh.
We're just scratching the surface here.
Yeah.
We're far from a complete understanding of how these models reason and make decisions.
But it's still exciting.
It is very exciting.
Yeah.
It's a step in the right direction.
Okay, so we've talked a lot about the potential of Quiet-STAR.
Yeah.
But earlier you mentioned that there are some practical limitations,
Yeah.
like the computational demands,
Right.
especially generating those thoughts for every single token.
Yeah, that can get pretty expensive.
So do you think there are ways
Yeah.
to make this approach more efficient?
Yeah, definitely. So one idea is to actually train the model to predict when it needs to generate a rationale.
So instead of just doing it all the time,
Exactly.
it would learn to be more strategic.
Yeah, like only think when it really needs to think.
Okay, so it's like recognizing when something is hard and it needs to like really engage.
Yeah, exactly.
Okay, so it's kind of like...
It's learning to allocate its resources more efficiently.
Right, like a human.
Exactly.
We don't think about every single word.
Right, we kind of skim over the easy stuff.
Yeah.
And then really focus on the parts that are tricky.
So we're teaching these models to think about thinking.
Yeah, it's like metacognition for AI.
I love that.
Yeah, it's pretty wild.
Okay, so to wrap things up,
Yeah.
this Quiet-STAR research, it's really pushing the boundaries
It is.
of what language models can do.
Yeah, it's a really exciting...
Moving beyond just like generating text.
Right, it's about understanding the meaning.
Yeah, and actually reasoning.
Yeah, solving problems.
It's really incredible.
It is.
So for our listeners,
Yes.
if you want to learn more about this, the paper is called
Quiet-STAR. Language models can teach themselves to think before speaking.
It's available online.
Yeah, you can find it with a quick search.
Yeah.
Go check it out.
And as always,
Yeah.
we encourage you to form your own opinions.
Absolutely.
Keep exploring these topics.
Yeah, keep learning.
Keep thinking.
Yeah, and keep those thoughts flowing.
All right, well, that's it for this deep dive.
Thanks for having me.
It was great having you.
Yeah, this is fun.
We'll see you next time.
See you later.
Bye.
Bye.